start with a few little updates. So I've gotten to grade a few tests. They're looking good. Nothing standing out as being a huge problem. I'm also working, I got a lot of submissions last night, so I'm working through those as quickly as I can. I'll get those out soon, hopefully. But as I do that, I wanted to let you know that all of the stuff for the Galactic Science Badge is open. I'm sorry if I flooded your Canvas yesterday with new assignments, but it should all be the kind of similar stuff to what we've seen so far. Same kind of homework situation. The one thing that's different with this badge is there are fewer reading quizzes because this badge includes that student choice section. So for the student choice, there won't be any readings, which means there won't be any reading quizzes. So if you want to get full homework points for this badge, you can't just do reading quizzes and the homework. You need to do one of these extra projects. Just to point that out. You can still get 100 points for this badge without getting 25 homework points, so you don't have to do one of those, but this is the only one where you can't get 25 points just by doing reading quizzes and the homework. There are new labs, which I will start opening up today. I think if they aren't already, this one will be a good one to start out with. This Milky Way lab will start to cover today. So if you want to try one of those tonight, I will be available. This one's going to be tricky. This is the only one that's going to be tricky. The rest are all stuff you can do in your house with just a computer. This one requires some extra equipment, and I don't know how well it'll work. So if you skip one, I would skip this one. Sorry. This last section, it's harder to build labs to work with it. And then there's all of our participation points, and then there will be a test on November 19th. So any questions about our last badge? I'm very excited for this one. I'm an extragalactic astronomer. I study nearby galaxies, so I love talking about galaxies. And then we get to end by talking about the current NASA missions. That was one thing that people voted for. Aliens, which is always fun, and then dark matter. So all very good subjects to wrap up our semester. Not seeing any questions in the chat. This is just kind of similar, a place where I can try to keep up where your points are. So it'll be, there's no submission for this assignment. It just is a place that has links to all of the assignments that you can get points. And I will try to keep it updated at least once a week or so as we go through. Okay, we have a few things to finish up when we talk about stellar corpses, and then we will jump into talking about galaxies. But I wanted to make sure we did just go over a few of these last things with stars and what we see when we look at what happens at the end of a star's life. So before our test last week, we talked about the Crab Nebula, where we had a big star that exploded, its core collapsed into a neutron star, and we were measuring kind of the ejected material outside of it. And so neutron stars, if they rotate, we can get something called a pulsar, which is a cool astronomical object that has just these rotating radio jets. So our neutron star is that very, very dense core of a star. So 10 to the 57th neutrons squished together into a tiny 21-kilometer ball. So I say tiny because it's very, very high density. So it's tiny for that number of neutrons. 20 kilometers is still about the size of an average city. So about Denver is 20 kilometers across, but small for the center of a star. For the most part, neutron stars don't emit any visible light, but this can change if they start to rotate and there's a few charged particles at their surface. So charged particles, if we're rotating, if there's moving charged particles, we get magnetic fields. So rotating charged particles, magnetic fields. If we have our neutron star spinning, there will be magnetic fields. But some charged particles might escape. As they escape, we get radio jets out of the poles of these stars. And because they rotate so fast, we can see these kind of flashes in the radio. So we can think of this almost like a lighthouse. So if the rotation of the neutron star is correct, so we're kind of coming in and out of the beam, we see flashes of radio light as the neutron star rotates. So we can measure how the rotation rates of these neutron stars are changing with time. And we can also use these rotations to get an idea of the size of the neutron star, which is how we know they're about 20 kilometers across. They rotate incredibly fast. So one rotation every 0.0001 to 10 seconds. So if you can imagine having a ball the size of Denver and spinning it, so it goes around once every 10 seconds or less. So very, very, very fast for something its size. And if we are in the right space where we're coming in and out of those kind of lighthouse beams, we'll see one flash of radio light. We'll see two flashes of radio light for every one rotation. So we can measure the rotation rates and we can see how these neutron stars will lose energy and slow down over time. So there's a pulsar in the center of the Crab Nebula. We are seeing these flashes of radio light, so we're in the right location to be aligned with these poles. And we're seeing it slow down and slowly lose angular rotation energy over time, as it also moves through, is affected by tidal forces from the outer layers of the star and other objects nearby. So gravitationally, it's getting slowed down just by pulls from other nearby objects. So pulsars are just a cool way that we can study neutron stars and see some of the fastest or rotating objects in space based on these kind of jets of radio light that we see from them. Any questions there? Sorry. The other thing I wanted to talk about a bit, and this was something that a few of you were slightly confused about on the reading quiz for this last section, so want to go over this a little in more detail. Plus we didn't get time to talk about it. So if you have a binary star system, which a lot of star systems are in binary pairs where you have two stars orbiting each other, when one of them dies, it can start leaching material onto the other. So if they're close enough that when one of the stars expands into a red giant star, its outer layers will start to be far enough from it, far enough from the star that those outer layers are from, and close enough to its binary pair that the gravitational pull from the binary pair is stronger than the gravitational pull from the star. So it'll start losing its outer layers to the other star. So this would be similar if like the moon was close enough to the Earth that the ocean would actually start to leave the Earth and move to the moon. The ocean would be pulled up out of the Earth into the moon. The same kind of thing is happening, but now we have stars that are close enough together. One of them is expanding and it's losing its outer layers, and its outer layers are starting to fall onto its binary companion. And this is one of the reasons Algol, that initial binary star system, the demon star, it looks so weird. It's because it's sort of leaching material onto its companion as they rotate around each other, which causes all these weird bright flashes and changes outside of just the normal binary star variability. If you have the proper setup, you can get a binary star dumping mass onto a dead star, so a white dwarf or some other kind of dead star. So let's pretend we have a binary system with a G star and an F star. So this is back to our HR diagram, our spectral classes. If that was the case for our binary star system, which one is going to die first, the F star or the G star? So you should see a poll now where you can vote. Which star has a shorter life, an F star or a G star? This is, we have to think way back to our HR diagram, where we had only brave astronomers fight giant killer monsters. So with the blue O stars dying early, M stars dying last. Maybe 10 more seconds. Okay, so we're actually flipped. We're going to have our F star is going to die first because we have only brave astronomers fight giant killer monsters, so OBAFG. So F stars will have shorter lives. They will die first. So our F star will die first and our G star will keep hanging out on the main sequence for longer. So remember, bluer stars earlier HR classes, OBA will die earlier, GKM will die later. F is that kind of middle, so F will die before a G star. Does that make sense? And this was, we had to think kind of way back to answer this, so yeah, but this might be a good reminder if you haven't taken the test yet. So our F star will die, it will become a binary, it will go through its giant phase and become a white dwarf with a planetary nebula. As that's occurring, the G star is still kind of chugging along on the main sequence, but eventually it will run out of hydrogen to fuse as well, and it will start to go into its giant phase. As it goes into its giant phase, if it is close enough to that white core remnant from the other star, it can lose some of its outer layers. Some of those outer layers can get pulled onto the white dwarf. And that can actually cause some little sparks of fusion at the surface of the white dwarf, which will create something called a nova. So not a supernova, but a nova, where the white dwarf will momentarily get fusion at the surface. It has hydrogen, it's hot enough to fuse hydrogen, and we get these bursts of fusion, bursts of brightness in the white dwarf called nova that occur shortly and then putter out as it quickly burns through all this fuel. If the binary system, if the white dwarf star accretes enough mass, pulls enough mass from its companion, it will explode in a type 1a supernova. So this is if it's pulling material, the G star is still expanding, the white dwarf star is still pulling some material from that G star, and it starts, maybe it started at 1 solar mass, the white dwarf star, and it's pulled material, and all of a sudden it hits 1.4 solar masses, which is our Chandrasekhar limit. We cannot have a white dwarf star above 1.4 solar masses. So once we hit that limit, our white dwarf star will explode in what we call a type 1a supernova. So this is why the type 1a supernova have to occur in binary systems, because you have to have one star that is a white dwarf. That white dwarf star has to pull material from its companion, surpass that 1.4 solar mass limit, and then explode. The really, really cool thing about type 1a supernova, and we'll use these as we study galaxies, is that they are super, super bright, they're supernova, but they're always the same brightness. So they're always, when the white dwarf star hits 1.4 solar masses, it explodes. So it's the same amount of material, the same type of material-ish. It's these white dwarf carbon stars. So they're always the same brightness. So we can compare how bright they look to how bright we know they must be to get a distance. So we call these a standard candle. They're always the same brightness. They're always the same standard brightness. And we can compare, just like we did with the Cepheids, we can compare how bright they look to how bright they are to get a distance to a type 1a supernova. They're bright enough too that we can observe them not only in our nearest neighbor galaxies, like the Andromeda galaxy, but also in some more distant galaxies. So it's a really nice way to get pretty accurate distances to fairly far away galaxies if they have a type 1a supernova. Kind of need that to be true for it to work. The way we distinguish between a type 2, so a core collapse supernova, so a Type 2 supernova, giant star collapses, explodes, and you're left with a black hole or a neutron star. Type 1a, white dwarf star pulls material from its companion, surpasses that 1.4 solar masses, explodes. So that's our two types. We can tell the difference by looking at the spectra of the supernova. Though type 1a is an exploding white dwarf star, so it doesn't have very much hydrogen. We don't expect to see any hydrogen lines in a type 1a supernova. Instead, we're going to see the carbon, oxygen, and silicon left over from the fusion processes that happened in this star. So this is our type 1a spectra. Let me get my pointer up here. You can see there's not really any hydrogen lines. There's some helium lines, some oxygen lines, some silicon lines, but there's no hydrogen lines. In the type 2 supernova, we still have those outer shells of hydrogen gas in our massive star that looked kind of like an onion. So there were different layers of heavier and heavier elements till we got to that iron core where we couldn't fuse further. So we will still see hydrogen emission. There will still be hydrogen gas. Type 2 supernova will have strong hydrogen lines. And this is how we can tell the difference. When we see a bright flash of light, if we get a spectrum for it and we don't see any hydrogen lines, then that might be a type 1a supernova. And that might mean that we can use it as a standard candle to get a distance to whatever galaxy we see that go off in. Any questions about type 1a supernova? And I've got the chat open too, I should say, if you want to throw them in there at any point. So that's kind of where I wanted to end with the stellar death. Now we can transition to start talking about galaxies. So like I said, these are kind of my favorites because they're what I study. I think galaxies are just super, super cool. So far we've talked about planets, which planets are really awesome too. Our solar system is amazing. It's the only place we can really send probes to. So it's really cool to talk about the other planets. And stars are awesome too because I couldn't study galaxies if they didn't have stars in them. But galaxies are just really pretty to look at, and they have stars and gas and dark matter, and I just think they're super awesome. So I'm really excited that we get to start talking about them today. And just like we started our discussion of stars by talking about our own star, the sun, we're going to start our discussion of galaxies by talking about our own galaxy, the Milky Way. Of course, when I talk about the Milky Way, I am not talking about the candy, I'm talking about the galaxy. So the Milky Way is the name for the galaxy that we are in. First little question for y'all. This is possibly an image of the Milky Way. I want you to tell me, and I'm just going to have the chat open, so I don't have a quiz for this one. Or a poll, sorry. Is this a real image of the Milky Way? Is this a real picture or is it fake? Would I show you a fake picture? And another thing to think about is, can we take a picture of the Milky Way? So I'm seeing one fake, a couple fakes. Yep, this is very much fake. And it's exactly the point that Cameron made in the chat. We don't have a selfie stick long enough to take a picture of the Milky Way. So that's my bad joke. I'm sorry. I will try not to make too many. Although we're 2/3 of the way through the semester, so hopefully you're used to me by now. But we have not sent anything out into space that has gotten out of the Milky Way. So the furthest thing that we have sent away is Voyager 1, Voyager 1 and 2, which are both kind of just getting out of our solar system. So our solar system is a teeny, teeny bit of the Milky Way, which is this giant galaxy that's thousands of light years across. So instead of a real picture, we can't take a real picture of the Milky Way, but we can use a lot of different methods to make nice models of what the Milky Way would look like if we were able to send a probe out of it and take a nice picture looking back. What we do see of the Milky Way is instead something that looks much more like this. So if you've ever been out camping somewhere where there's not very much light pollution, you might have seen a kind of strip in the sky that is our Milky Way. This is a pretty long exposure image taken from high on a mountain in Chile. So not very much light pollution, also high enough up that there's less atmosphere. So you can look through and see more of the Milky Way and get just a better idea of the galaxy we are in. Some other little fun things you can see in this image. So this bright blob up here, that's Jupiter. And also there's a little fuzzy bit down here. This is the Large Magellanic Cloud, which is one of the Milky Way's satellite galaxies. Unfortunately, we can't see that from the northern hemisphere, but if you do ever go down to the southern hemisphere, or go to the southern hemisphere, not down, you can see the large and small Magellanic Clouds, which are two satellite galaxies of the Milky Way. And they look kind of like little fuzzy blobs on the night sky. So I went to a conference in Australia last year and did some backpacking around Tasmania. And while I was there, we could see the large and small Magellanic Clouds, which was just super cool. From the northern hemisphere, you can also see the Andromeda Galaxy, which is a nearby galaxy. So you can see a galaxy outside of the Milky Way, but it's not going to look like a fuzzy blob. It's going to just look like a star, essentially, in the Andromeda constellation, because it's far enough away that it's not a satellite galaxy. It's not rotating around the Milky Way. It's another separate galaxy, which we will talk a lot about later, because it's our closest galaxy. But right now, we're going to take a break to do a little activity to figure out how we know where we are in that big spirally structure, how we can get these ideas of what the Milky Way looks like, despite the fact that we are inside of it. So this is going to be our first participation activity for our Galactic Science Badge. It's called Day 15, the Milky Way. And we're just going to do this little Where Are We quiz. Let me see if I can show this. So the idea for this is you're going to look at some pictures of the Milky Way at different wavelengths and think about what that might tell us about where we are in this disk. And then you're going to use the position of globular clusters, which is what's down here. So this is one of the ways that Harlow Shapley, we will talk about this more after, but I want you guys to do it first, figured out where we are in the Milky Way. So you're going to make a histogram of the position of globular clusters. So there's a few ways you can do this. You can use kind of any sort of spreadsheet tool will allow you to make histograms where we're showing number on the y-axis. So a number versus how many are in that bin. So you're going to measure the angle to the different globular clusters around the sun. So this one would be at an angle of 90. This one's about halfway between 90 and 180, so about 225, and just kind of going around doing your best to measure angles to these globular clusters for both case A and case B, and then make a histogram. You can also do that just with a pen and paper. So this would be kind of a histogram that I'm sketched out where I'm going to make an X for every globular cluster that I measure between 0 and 45. So for case A, there's one between 0 and 44. There's also one, it looks like 45 to 90, so I would draw another X for that. And then if there were two in one bin, I would just draw one X above that to show that there were two in that bin. So this is the idea, a histogram where we have a measurement on our x-axis and then just the number of globular clusters we see that match that measurement on the y-axis. Like I said, this is also something, if you're working in a spreadsheet, you click your column, insert, chart, and then you have to go to chart type and scroll down until one of the options is a histogram. So, and then I messed around a little bit with my, my axes to get the right bins. So you can change your bins where I wanted every 45 degrees. So either way works, whatever you like better. As I open breakout rooms for us to work on this, does anyone have any questions? I am not hearing anything, so I'm going to go ahead and open the breakout rooms, and grab me if you have a question. I'll be around to bug you as you work on this.